This second lab, I'm going to begin with an overview what this lab is about. We've seen that R is a functional language. Everything that happens in R happens as a consequence of as a function, and we've seen 3 of them. They're shown there. Every time you load up R, you get a number of functions that are built into base R. But those only go so far. And what we will rely heavily on in this course are additional packages built by data scientists. And these additional packages come with them functions, some built-in data frames, and some documentations. And one of the really important packages we're going to be using is ggplot2, and we're going to use that package today because that will give us access to the data frame MPG. So, the first step in data visualization is typically data manipulation. And you have to be really good at that if you want to be really good at data visualization. In the last lab, we talked a bit about data frames. And in this lab and in all the rest of the labs, we're going to be working almost exclusively with data frames, because by doing so, that will enable us to work with these third-party packages in a very efficient way. So, this is a really important slide, and this slide shows the data frame MPG. And here we have the 11 variables that are present in the data frame MPG, and that data frame reflects some information on vehicles, motor vehicles. So what are these variables? Well, we got the manufacturer. There's 15 of those. We have 38 different models. Displacement is the size of the engine, the year in which the car was built, either 1999 or 2008, the number of cylinders, the drive, fore, rear, or front wheel drive, city and highway mileage, and the type of fuel. This column is really important. And in this column, we see the type of variable. And we've got characters, and we've got a num, and we've got a bunch of int. And we can come down here and see that these variable types fall into one of 2 categories. Either this category or this category. And the first category, we've got either characters or factors. They behave very similar. Now, in our particular data frame MPG, we don't have any factors, but we'll be seeing those later on. If you've got something that's a character or a factor, the variable is a discrete variable. So if we come up here and think about manufacturer or model, for example, they can only take on discrete values. The notion of quotes, if we look at manufacturer or if we look at model and we look at some of the levels, like there's our Audi, notice that it's in quotes. Audi is in quotes, or the model A4 is inside quotes. So that's these guys here. Now let's think about the ints and the nums. The ints or the nums, they are continuous variables. So if we think about something like displacement, the size of the engine, that's going to be a continuous variable. Or city or highway mileage, that's going to be a continuous variable. Also note no quotes. No quotes. So in contrast to manufacturer and model, where you see these little quotations, if you look at city and highway mileage and the different levels, there's no quotations surrounding them. Why is this distinction? Why is this distinction between these 2 groups of variable types so important? It's because everything that happens in R happens as a consequence of function, and the function is likely going to expect something from this group or something from this group, and if you feed it something from the wrong group, nasty things are going to happen. So, next topic is this notion of chaining commands. How we're going to link commands together to get things done. So let's assume we're going to begin with a data frame that we just saw, MPG. And we want to make a new data frame called MPG1 that's going to be pretty much the same as MPG with the following changes. It's only going to have two variables, drive and city. It's going to be filtered so that the only records that are in MPG1 are going to be those for which city mileage is greater than 22. And then I want to change the value of city. I want to update it by increasing it by a value of 10. Here's a bunch of code that would enable me to do that. And don't pay very much attention to this code because we're not actually going to use it. I just want to focus on the process. And one way we could accomplish our goal would be to start off with MPG, write a bunch of code, make this new data frame df1, use that as a starting point, write a bunch of code to create df2, use df2 as a starting point, write a bunch of code, and create MPG1. I'm not focusing on it because that's not what we're going to do. This slide shows what we're going to do, and it involves this process of chaining. So, my goal is to produce MPG1. And here you see the assignment operator. And what that means is, what's MPG1 going to consist of? It's going to be assigned everything that's to the right of this assignment operator. There's another way to think about this. An alternative way to think about this is that in order to create MPG1, I'm going to start with MPG, and then I'm going to do a bunch of stuff. And that's where this operator comes in. This operator is referred to as the piping operator. And it consists of the percent sign, the sign here, another percent sign. A really useful keyboard shortcut is Control-Shift-M. So every time you see this piping operator, what should go through your mind are the words "and then." So, to create MPG1, there's my assignment operator. And if you want a keyboard shortcut for that, there's the keyboard shortcut. It's worth knowing that you could use an equal sign rather than an assignment operator, but that doesn't appear very elegant, so normally we don't. But anyways, to create MPG1, I'm going to begin with MPG and then. So every time I see this, what goes through my mind are the words "and then." So I start off with MPG, and then I use this particular function to retain only those two variables. Then I continue on with the piping operator, and then I filter to retain the records that I want, and then I continue on to create or update the value of city mileage. One thing to note, all this code here could have been created, could have strung that out as a single line. But I decided not to do that. I decided I wanted to have 3 separate lines because there's 3 separate operations that I want to perform. By leaving the piping operator at the end of each line, that was a signal to R to keep on going. There was more code that needed to be evaluated. So this is just a reference slide that talks about some of the functions that are in this third-party package. So there's this third-party package, dplyr, that's going to be really important in data manipulation. It has a large number of functions. These are the ones that are going to be most important for the labs in this course. I'll go over these. These are less important. If you're in a big rush, you really don't have to worry about these for now. So these guys are the really important functions. Let's go through them. And the first one is arrange. And anytime you see the word arrange, what you should be thinking of is sorting. So the arrange function is going to sort the records in the data frame. So here we have a bunch of code that's going to create MPG1. And down here in our table, we've got a description of what MPG1 is going to be. So in this particular case, we're going to create MPG1 by beginning with MPG. There's our piping operator. And then, because of our piping operator, we're going to sort with the arrange function, and we're going to sort based on the variable displacement. So MPG1 is going to have all the records and all the variables of MPG, except that they're going to be rearranged. They're going to be rearranged. They're going to be sorted based on this variable displacement. Now, by default, the arrange function sorts from smallest to largest by putting DSC in front of DSPL. It's going to reverse that, so it sorts from largest to smallest. Just to reiterate something that was brought forward in the previous lab, notice the fonts. Courier font here, Calibri font here. This is an R keyword. This could be anything. I could sort on displacement. I could sort on highway mileage, city mileage, any sort of continuous variable. But not only can I sort on continuous variables, int or num, I can also sort on discrete variables, chr or factor. And we can see that here, where I'm sorting based on model, which is a character. By default, the sorting is going to be in alphabetical order from A to Z. Down here, I'm doing two sortings. Doing the first sorting here, and then separated by a comma, a second sorting. So the initial sorting is going to be based on model in reverse alphabetical order because I preceded it with a DSC function. And then when there's ties among models, there's going to be a secondary sort done on the basis of displacement. Another reference table for logical operators. And most of these are fairly straightforward. Less than or equal to, greater or equal to. And this is the one that's really important. This is the one that often throws me. If you're performing a logical test, if you want to see whether two objects are exactly equal, you need to use a double equal sign. A single equal sign will not work. The reverse of a double equal sign that says is identical to is an equal sign preceded by an exclamation point which says is not equal to. And here we've got a couple of connectors, a couple of joiners, the OR joiner and the AND joiner. So if I wanted to do a logical test that involved X or Y, then what I need is this vertical line here. And where do you find that vertical line? If you look at your keyboard, upper right-hand corner, locate the backspace key. Directly beneath that is the vertical line. Here is the ampersand, represents AND. Where do you find the AND? If you look at the top row of your keyboard, associated with numeral 7 is the AND operator. So, we're going to use those logical tests in our next function, which is the filter function. So filter is going to be retaining or dropping records based on the value of some variable in the data frame. So, first example, we're going to create a new data frame called MPG1. It's going to be based on MPG, and it's going to be filtered. It's going to be filtered according to drive. And what we want to have happen is that MPG1 should only contain some of the records of MPG. It's going to have all the variables, but only some of the records. Which records it's going to have? It'll only have those records for which the value of drive is equal to 4. So what we're doing is we're performing a logical test here with a double equal sign so that the only records that are retained are those for which drive is equal to 4. So, two things to note. It's a logical test. We need a double equal sign. Second thing to note is the quotation marks. And the quotation marks are necessary because this variable drive is one of these guys. In the next example, we're also doing a filtration, but now we're filtering based on cylinder. So we want MPG2 to have all the records of MPG1 for which the value of cylinder is greater or equal to 5. Note that there are no quotation marks around the 5, and that's because cylinder is one of these guys. The next two examples show the use of that joiner operator, the or the and. So in the first instance, we want to filter MPG to contain records that meet either one of two criteria. Either the cylinder is less than or equal to 6 or highway mileage is greater than 28. And in the next instance, we want to use and, so that the only records that are retained are those for which the cylinder is less than or equal to 6 and the highway mileage is greater than 28. In this example here, up here we use the double equal sign for equals to. Here we've got the equal sign preceded by the exclamation point not equal to, so the only records that will be retained are for those for which the fuel does not equal R. Let's say we wanted to filter the data frame to only retain these three different models, the Passat, the Civic, and the Malibu. One way to do that would be to use this approach with a whole bunch of these or symbols. So we'd filter retain model is equal to Passat, or model is equal to Civic, or model is equal to Malibu. That would be a lot of typing. An alternative is to use this code here. And I'm just presenting this as a recipe. So you just accept it as it is. If you want to know more about it, you can go to Appendix 19 and you'll get all the gory details. But if you're happy with a recipe, this is what will work. So you got a filter based on model, and this is a key thing. It's all in Courier, percent in percent. And then you specify the models that you want to retain, and you do that using the C that we saw in the previous lab that stands for concatenate, and then we create a vector with the C, so there's the open and the closed parenthesis associated with the C, and then we list the three models that we want inside quotation marks because they're characters, and separated by commas because what we're doing is making a vector. Select. So when we did filter, we were adding or dropping records. Now we're going to add or drop variables. So in the first instance, we're going to make MPG1. It's going to be based on MPG, and it's going to retain only two variables, highway and city mileage. So whereas MPG1 would have 234 records and 11 variables, MPG is going to have 234 records and only two variables, the ones that are specified by the select function. We can also use the select function to drop variables by using the minus sign. So in this case, MPG2 is based on MPG. There's our piping operator. We're going to specify these two variables contained as a vector associated with the C function, but by having this negative sign in front of them, that's going to cause these two variables to be dropped. An alternative way to do this would be to use the select function, but put a negative sign in front of each one of those variables. Down here, there's a bit of a warning that sometimes select doesn't seem to work very well. And it may be because you're using another package that also has a select function which is conflicting with the select function of dplyr. If that seems to be the case, then one way around it is to use this code here, which informs R that the select function that you want to use is that which is associated with the dplyr package. Mutate. Mutate is a really important function, and every time you see the word mutate, the word you want to think of is the word create, because mutate is the function we use to create new variables. And here we have the general overall syntax. So we're going to use the mutate function, and there's its open and its closed parenthesis. And within the mutate function, we begin by specifying the name of the new variable that we want to create. Then we have an equal sign, and then we say, okay, we want to make this new variable as some function of a specified old variable. So now we're going to go over some examples. So In the first example, we create mpg1 by starting with mpg, and then with our piping operator, we're going to use mutate. We're going to use mutate to create this new variable. How is it going to be created? It's going to be created by taking the value of year and adding 5 to it. In this next instance, note that the variable year is on both sides of the equation. So what this code is going to do is it's going to update. It's going to update the value of year. So if we compare this line with this line, in this first instance, MPG1 is going to have all 234 records of MPG, but it's going to have this new variable, a 12th variable called year 1. In the second instance, MPG2 and MPG are both going to have 234 records and 11 different variables. It's just that the value of year in MPG2 is going to be 5 units larger than the value of year in MPG. And the final example is just meant to demonstrate that having created a variable by the mutate function, we can actually use that variable in the same mutate function as long as we separate the operations by comma. So we start off here. There's a mutate function with its open and closed parenthesis. We create a new variable called year 1, and then after the comma, we use year 1 to create a new variable called year 2. Then following a comma, we use year 2 to create this new variable called year 3. Conditional mutate. Now, in the previous example, where we started it off with MPG and made MPG1 by mutating to create the new variable year 1 by adding 5 to year, in every instance in MPG1, the value of year 1 is going to be equal to year plus 5. Now what I want to do is something a little bit different, and it's probably best explained by an example. I want to use mutate to create a new variable. And the name of that new variable is going to be size, and size is going to be one of these character variables. And size is going to be a word, and it's going to be one of 2 words. Either the variable is going to have the value of the word small, or it's going to have the value of the variable big. But the whole idea about conditioning a mutation is whether or not it's a value of small or a value of big is going to depend on the value of displacement. So if displacement is less than 4, then I want the value of the variable size to be the word small. Alternatively, if the displacement is greater or equal to 4, then I want the value of the variable size to be equal to the word big. So it's conditional mutation in the sense that we're creating a new variable with mutate called size, that it's going to take one of these 2 values, small or big, but it's conditional upon the value of the variable displacement. Function we're going to use to accomplish that is the if-else function. So here is our if-else function, and there's our if-else function, and there's its opening and closing quotation, and it takes 3 arguments, 3 different arguments. And the first argument is a logical test. So we're going to perform a logical test. The outcome is going to be either true or false. If it's true, the function is going to return this value. If the outcome of the logical test is false, then the function is going to return this value. So here's an example of the if-else function. So the logical test comes first. So what the if-else function is going to do is it's going to look at every record in the data frame, and it's going to ask this logical question. Is the displacement less than 4? And there's only 2 possibilities, true or false. If the displacement, in fact, is less than 4, if the logical statement is true, then the if-else function will return the word small. Alternatively, if the logical test is false, then the if-else function is going to return the word big. So to accomplish the goal that we want to accomplish, this is the code that we're going to use, and it consists of the if-else function nestled inside of the mutate function. So create a new data frame called mpg1 based on mpg, and then we're going to use our mutate function with its open and closed parenthesis. The name of the new variable we want to create is the word size. So we begin by specifying the name of the variable we want to create, and it's going to be some function of, well, other variable, and here we see that. So to determine the value of size, we use our if-else function with its 3 arguments. So the first argument evaluates every record in the data frame MPG and asks the question, is the displacement less than 4? If the answer to this logical test is true, then size is going to be equal to the word small. Alternatively, if this logical test is performed and the answer is false, then big is going to be the value of size. Note quotation marks here. That's because we're creating a variable that is a character. Just a little note about different ways in which equality is expressed, because it can get a bit confusing. One way is the assignment operator. A second way is the single equal sign if you're doing mathematical calculations, and thirdly, the double equal sign for testing of a logical relationship. And we see those all 3 down here, where we create MPG1 by assigning to it what's on the right-hand side. So you think of MPG1 is going to consist of everything that's to the right of the assignment operator. Down here, we've got some mathematical calculations, and here, and note the difference between a single equal sign and a double equal sign, we have a logical test. So we're performing a logical test, and we're asking the question, is the value of drive exactly identical to the value f? Group by. Just an introductory slide to make the point that group by is really important, and it's used in 2 different contexts, with mutate and with summarize, and we'll begin using group by together with mutate. So, as always, mutate creates, but when group by is used with mutate, then the creation of this new variable is going to happen independently for the different levels of the grouping variable. That's just a bunch of words. To think about it more concretely, we can think about the output that happens when we use group by with mutate. We'll make a new data frame in terms of how many records it's going to have. It's going to have all the records of the old data frame, and it's going to have all the records, all the variables of the old data frame, and whatever new variables are created by the mutate function. To show this, I'm going to begin by making a new data frame. I'm going to make a new data frame called MPG1 that's like MPG, except it's only going to have these 2 variables. So whereas MPG has 234 records and 11 variables, MPG1 is going to have all 234 records, but only these 2 variables that are retained as a consequence of using the select function. So I'm going to begin with this MPG1 that I just created with 234 records and only these 2 variables, drive and city mileage. And what I want to do is I want to create, using the mutate function, this new variable that's average city mileage. But here's the trick. The trick is that in MPG, there are these 106 of those vehicles are front-wheel drive. On average, those 106 vehicles have a city mileage of 19.97. In the initial data frame, there are 103 records associated with four-wheel drive vehicles. Their average city mileage is 14.33. There's 25 vehicles that have rear-wheel drive, and their average mileage is 14.08. So you can see what I'm trying to do. What I'm trying to do is I'm going to use mutate to create this new variable. but the creation of this new variable is going to occur independently based on the level of drive, so that all the front wheels, all 106, get 1997, all 103 four wheels get 14.33, and all 25 rear wheels give 14.08. So here's the code that does that. I'm going to create MPG2 by starting off with MPG1. There's my piping operator. I'm going to group by drive, and then going to use mutate to create this new variable called city average, which is just the mean of city mileage. So one way to think about it is, if I compare the new data frame with the old data frame, I'm going to have all of the records. I'm going to also have all of the variables of the old data frame. But by virtue of using the mutate function, I'm going to have created this new variable, city average. But the key is, because I preceded mutate with group by, because group by preceded mutate, when it comes time to calculate city average, it's going to be done independently. So all the front wheels get 19.97, and all the four wheels get 14.33, etc. Now we're going to use group by again, but instead of combining it with mutate, we're going to combine it with summarize. And that's going to enable us to generate some summary statistics. Typically in these labs, we're going to be doing the average. Occasionally, we're going to be using a count. So one way to focus on this is to think about what is the ultimate outcome data frame look like relative to the original starting data frame. Relative to the original starting frame, the ultimate, the final data frame, how many records? It's only going to have one record for each value of the grouping variables. How many variables it's going to have? The only variables that are going to be present are those that are specified within group by or created by summarize. So if you think about what the word summarize means, it means make smaller or compress. So what we're going to do is we're going to start once again with this MPG1 that has 234 records, but only those two variables, drive and city. And I just want to know, okay, for the front wheel, the four wheel, and the rear wheel drive, what's the average city mileage? And group by, together with summarize, is going to enable me to make this summary data frame. So here's the code. I say I want to make summary statistic city average, which is equal to the mean of city. But I want it done separately for the three different drives. So I start off with this really big data frame, MPG1, my MPG1, and I wind up with MPG3, which is very much a summary data frame. One way to think about it is, how many records am I going to have? How many records am I going to have? I'm going to have one record for each value of the grouping variable. So if I group by drive, and there's three levels of drive, how many variables am I going to have? Excuse me, how many records am I going to have in MPG3? How many records am I going to have? Only three. 4, F, and R. Because up here, I group by drive, and there's only three different levels of drive. How many variables am I going to have? The only variables I'm going to have are those that are specified within the grouping function, which is drive. Okay, so there's my drive. Or created by the summarize function. Summarize function created city average. There's city average. I went through the lab manual, and I identified for the entire course a bunch of slides that I thought were really, really important, and I gave them that symbol. And what this particular slide is meant to do is to compare mutate with summarize when used in conjunction with the group by function. So in both cases, I'm going to begin with MPG1, this relatively small data frame that has 234 records and two variables. And then I want to compare group by with mutate and group by with summarize. So we begin with group by associated with mutate. So I'm grouping by drive, and then I'm using the mutate function to create this new variable called city average. So anytime you use group by mutate, what is the final data frame going to look like? How many records is it going to have? Well, it's going to have all of the records of the original data frame. So MPG2 is going to have all the records of MPG1. How many variables is it going to have? It's going to have the initial variables of MPG1 and whatever new variables are created by the mutate function. So it's going to have this additional variable, city average, created by the mutate function. But the point is, because we used the group by function prior to using the mutate function, when it comes time to generate this new variable city average, it will occur separately for the different levels of the grouping variable. So that all the front wheels get one value and all the fore wheels another value, etc. Down here, we have group by combined with summarize. And one thing to note is if we compare this block of code with this block of code, they're essentially identical except for this one word, mutate versus summarize, but the output is radically different. When we use the summarize function, what we're going to generate is a compressed or much smaller data frame. So when we make MPG3 based on MPG1 together with group by and summarize, what we can think of is, okay, how many records are we going to have? We're going to have one record for each level of the grouping variable. So if we group by drive, we're going to have only 3 records corresponding to the 3 different levels of drive. How many variables are we going to have? The only variables that are going to be present are those that are either specified within the grouping function, so we're going to have drive, or produced by the summarize function, which means we're going to have city average. So those are the only 2 variables that we're going to have. Okay, so we've talked a bit about summarization. What sort of summary values are available to us? This is another reference slide, and so we can see the summary statistics, and this is the name of some sort of a continuous variable, either an INT or an NUM. Could be something like the number of cylinders or the displacement or highway or city mileage. So what are some of the summary statistics available? Mean, sum, min, max, median, range, standard deviation, variance. And we can also do a count of records. But what's interesting about this function is there's nothing inside the parenthesis. It's got the keyword n, but nothing inside the parenthesis. What's going on? Well, think about it. It's counting. It's counting. So if it's counting, how many records are there associated with the variable displacement? 234. How many records associated with the variable city mileage? 234. Highway mileage? 234. Doesn't matter which variable you choose, you'd always get the same answer because the data frame is rectangular. So that's why there's no requirement to have anything inside of the counting function n. So this just does a comparison between taking the mean or some other summary statistic as opposed to this rather unique counting statistic n. So we group by drive, we use our summarize function. What do we get? What we get is what happens always when we use group by together with summarize. How many records? We get 1 record for each level of the grouping variable. There's 3 drives, we get 3 records. How many variables do we get? The only variables that we get are drive, that's specified with the group by function, and city average, specified by the summarize function. In the case of MPG4, we go through the same process. The only real difference that I meant to show here is that, whereas up here, when we take the mean, we specify a particular variable, whereas down here, where I create the new variable count, creating this new variable count, the number of records, because I'm using the n function, there's nothing inside the parentheses. This slide shows that we can group according to multiple variables and we can generate multiple statistics. So now we're grouping by two variables, drive and cylinder, instead of just one. So what are the implications of that? Well, the implications are how many records are there going to be? Well, there's going to be one record for each of the different unique combinations of drive and cylinder. How many variables are going to be? There's going to be 4 variables. Drive, cylinder, city average, and count. And there they are. One thing about grouping. Once you've grouped a data frame, it's going to stay grouped. That may not be a problem under some circumstances. It may be. Later on, we're going to use this particular function to make pivot tables, and it doesn't work very well if it's used on a group data frame. Rather minor function we're going to briefly examine is sample n, which enables us to take a random sample of records. If you use this sampling function and you specify some number of records and you do it on a group data frame, then the number of records that you specify will be the number of records taken from each group. And later on in 582, you'll use a bunch of statistical packages, and some of those may work differently on grouped versus ungrouped data frames. So there may be value in using the ungroup function to undo the grouping process. Down here, we show some code that does that. So initially, I just create a new data frame called A, which is identical to MPG. And now I create another data frame called B, which is starting off with MPG, but then it groups by fuel. And then finally, I create a data frame called C, which starts off with B, my group data frame. And the important point is it shows the code that you'll type in to use the ungroup function to create a new data frame called C, which is just like B, except now that it's been ungrouped. And if you look at your environment pane, what you've seen is, okay, that A is just a basic data frame, but when you use the group function, you wind up with a group data frame. If you start off with the group function, then whack it with, start off with the group data frame and whack it with the ungroup function, then what you're going to have is going to be a data frame that's ungrouped, and that's shown here. Now, if you look at this, A and C are both ungrouped. C is ungrouped because of the ungroup function here, whereas B is grouped. Now, these two aren't exactly identical. There is this distinction between a data frame and a table data frame, but the distinction is really quite trivial based on the way in which they would print out. Now I want to look at the interaction function. And the interaction function can be used to generate a new variable, which is a combination of two older variables. So what I'm going to do is I'm going to use the mutate function to create a new variable called drive cylinder. And I'm going to do that by combining the value of the variable drive with the value of the variable cylinder. So I'm going to create MPG1 based on MPG and this code. And so in my initial data frame, MPG, I had the variable drive and city. So now, if I use this particular code and this interaction function to combine drive and city, drive and cylinder, then what's going to happen over here is there's my new variable, drive.sil, my new variable drive.sil. There it is, created by my mutate function, and it consists of a combination of these two variables here, drive and sil. So the F gets combined with the 4, there it is, separated by a period. And the R gets combined with the 8, there it is, separated by a period. And there's a little note down here that says by default, the separator is a period. If you don't want a period separating the value of drive from the value of cylinder, let's say you wanted a colon, there's the code that would do that. Use the interaction function, you specify the variables that you want combined, and then you say separate equals, and inside of quotes, you put the colon, And if that's the case, then instead of having these periods, you'd have colons as the separator. Now, many of you have probably worked with Excel, and if so, you may have come across a really neat function in Excel, which is called the lookup table. And in this next series of slides, what I'm going to try to show is how we can replicate Excel's lookup function in R. So here's the goal. We're going to start off with MPG with its 234 records and 11 variables. And one of those variables is called manufacturer, and it's got 15 different manufacturers. And where I want to wind up is with MPG1, that's going to have all the 11 variables and all the 234 records, but it's going to have a new variable. What I want to do is I want to attach this new variable to MPG to make MPG1. So what is this new variable? Well, this new variable country is the country in which the head office of the manufacturer is located. And here we see for each one of those manufacturers the country in which the head office is located. So the whole idea of a lookup table in Excel, or as we're going to see it in R, is we're going to start off with this data frame, and I want to add this new variable which shows for each manufacturer where its head office is located, and that's going to be done based on the information in what's known as a lookup table shown here. So that's just an overview of what we're going to do. So here's a very simple example of how this might work. So we're going to start off with a very simple data frame called G that has manufacturers, but only these three. And where I want to wind up with is I, that's the same data frame, models and the three manufacturers, but now has the country of origin. So the Audis are built in the European Union, Fords in the USA, Hondas in Japan. So what I'm going to need is a data frame like this that shows that relationship. For each one of these manufacturers, it's important to note that the word here has to be exactly the same as the word here. For each one of these manufacturers, we want to have the country in which the head office is based. So in this data frame, I'm going to need the three different manufacturers. They have to be the three manufacturers here. Each one of these manufacturers, Audi, Ford, and Honda, should occur once and only once over here. In this particular case, I've shown these guys in alphabetical order. That isn't necessary. But the whole idea is that once I have this new data frame H in hand, I've got that data frame H in hand, I can combine it with the data frame G using the full join function. So what I'm doing is I'm creating the new data frame, the desired data frame I, that has this new variable reflecting the country of origin by using the full join to combine G and H. So how would it work in R if what I really wanted to do was start off with MPG and make some sort of a new data frame that's going to have all 234 records, all 11 variables, but now we'll also have this 12th variable that reflects the country where the head office of the manufacturer is located. How am I going to do that? Well, to begin, I'm going to go into Excel, and I'm going to create an Excel spreadsheet, and that Excel spreadsheet is going to be a comma-delimited file with a CSV extension. And that Excel spreadsheet is going to have the two variables. It's going to have manufacturer, that's going to match up with the variable manufacturer in MPG, and then it's going to have this variable named country that will be the new variable in the new data frame that I'm about to build. So I first have to make this data frame, and so when I make this data frame, The word here has to match up exactly with the equivalent word in MPG. I need all 15 manufacturers. They can only occur once and only once. As I mentioned before, here they're shown in alphabetical order. That's not necessary. Then I'm going to have this second column, and whatever variable name I give it here will be the variable name of the 12th variable in the new data frame that I'm about to build. So I do all this in Excel. I make my comma delimited file in Excel. And then what I'm going to do is I'm going to import it. Once I've built it, I'm going to import it into R using this read CSV function that we saw earlier. And once I have MPG in hand, and once I've got this data frame that I'm going to call lookup in hand, then it's very easy to make the desired data frame using the full join function to join up MPG, the initial data frame, with lookup, which is essentially that data frame there. So in terms of the particular code, I'm going to use the read CSV function to create this data frame called lookup. How is this data frame created? Well, I go into the C drive and the RTemp folder, and in there I'll find an Excel spreadsheet with the CSV extension that's going to have the 15 different manufacturers and the associated country of the head office. So once I've got this new data frame lookup, I just combine lookup with MPG using the full join function to create this new data frame MPG1. So what I'll wind up with is that which I desired, this new data frame MPG1 that has all 234 records, all 11 variables, and this new variable country that reflects the location of the head office. Switching topics once more to talk about pivot tables. Now earlier on we produced a table that looked like this. Produced a pivot table. And we had the 5 different fuels and the 3 different drives, and inside the body of the table with a number of records associated with each of those combinations of fuel and drive. And we did that using the xtabs function, and there's its open and close parenthesis, and within that function we specified the data frame, the comma, the tilde. As you recall, it's located directly beneath the escape function, and the 2 variables that we're interested in. We could do the same thing using a different function. This function right here that stands for quick pivot. In order to use that function, you'll have to install and load this package, the pivot table package. To produce the desired data frame, there is a function with its open and close parenthesis and a series of arguments, beginning with the data frame that we want to operate on, followed by, and again there's a whole bunch of commas here, the variables that we're interested in, and then the summary statistic. If we want the count of records, we're going to use n, because that's what gives us a count. Remember, when you use n, nothing is required inside the parentheses. These things, these quotation marks, are necessary. So if we do all that code, we get a very similar data frame to this one. So we've got our 5 different fuels and the 3 different levels of drive. But we can do more with qpivot than just count up records. The real power is that it will allow us to generate summary statistics. So for example, the average of city mileage. So what we have here is a pivot table that has the different fuels and the different drives, the average mileage, average city mileage associated with each of those combinations. The syntax to do that is there's a qpivot function, it's open and close parenthesis. I've spread it across 2 lines with a comma at the end of this line to tell R keep on going, and there's a bunch of arguments. We specify the data frame of interest. We specify the variables we want. We want drive and fuel. Then we specify the summary statistic. We want the average city mileage, so we use the mean function combined with the variable city. Notice all these things are in quotes. Then after our comma, I provide some initial information. Note the format. The font is entirely in Courier except for this little thing here, this .1. And so what this particular line does is it controls the number of decimal places. So you notice down here that you've got one decimal place, and that occurs because up here, the only thing you're allowed to manipulate in this code is this part right here. A 0.1 ensures there will be just one decimal place. Some modifications are shown here. In this pivot table, I want to have not only different fuels, but I want to have combinations of drives for front, rear wheel, as well as cylinder. And in the previous slide, there were these totals. There were these totals here that are actually misnamed because they're not totals. They're just the averages of whatever is going to be in this row. So the 14.3 would be the average of the 14.3, the 16.0, 9.3, and the 15.5. So what we're going to see in this example is the elimination of what are known as marginal totals if you don't want them. So the code to do that is we're going to use our qpivot function, and there's its open and close parenthesis occurring on a bunch of lines separated by commas. I want on the rows both drive and cylinder. So my initial argument is a vector with a C that includes both drive and cylinder inside the parenthesis. On the columns, I want fuel. Fuel is going to go in the columns. And in the body of the table, what I want is average city mileage. So it goes in the body. As in the previous instance, I only wanted one decimal point, so I did the 0.1. And then the way I got rid of those marginal totals was, after this comma, totals equals none. So we've seen a couple different ways to get summary tables. There's the pivot table and the data frame. And for the most part in this course, we'll be focusing on data frames, because data frames will be the starting point of data visualization. Sometimes in order to understand your data, you might want to use a pivot table, but as I said, in this lab for this course, data frame is going to be our real workhorse. And so you can see here the different codes that can give fairly similar results depending on whether you want a pivot table or a data frame. Just a note here, as I mentioned earlier, that if you've got group data, this pivot table with qpivot may not work very well, so you may need to use the ungroup function. Now we're back to slide 105 and a topic that is very important. So what we're going to discuss here is how to convert between wide and long formats, and we're going to use a new package. We've been spending a lot of time talking about the package dplyr. Now we're going to talk about a new package called tidyr, and it's going to enable us to go from wide or multivariate format to long or univariate format. And here we have two data frames that have exactly the same information. They differ in the shape of the data frame. So in this first data frame, we went out on May the 1st and got ozone, wind, and temperature readings, and did the same thing on May the 2nd, got the ozone, the wind, and the temperature. That same information is presented in this data frame. The only thing that's changed is the formatting. So there's the May 1st ozone, and the May 3rd ozone, and the May 1st wind, etc. The data is the same in both. This is called wide format because obviously the data frame is short and squat. This is called long format because the data frame is tall and skinny. This is sometimes referred to as multivariate in the sense that you can consider them to be multiple dependent variables, ozone, wind, and temp, Whereas in this instance, this second data frame, you can consider it to be univariate. Consider it to be univariate because in a sense there's only one dependent variable that's called y, and ozone, wind, and temperature are deemed to be predictor variables. So in order to demonstrate this process of going back and forth between wide and long formats, I'm going to use the data frame air quality, but I'm going to begin by a couple of modifications. The first is this thing here, which is just a recipe. It's not really that important, but the thing you remember about R is that it's case sensitive. The uppercase and lowercase, that matters. And to me, the simplest thing is to make all my variables have lowercase, and that's what this bit of code will do. So again, it's just a recipe. It's not critical for the general process. It's just a way of making sure that all my variable names are lowercase. And the data frame air quality has a whole bunch of variables. I'm only interested in a few, so I'm going to use a select function just to have those that I really think are important. So here's the process. My goal is to go from the wide format into the long format. And in order to do that, there's three different things that I need to focus on. The first is, what are the variables? What are the variables that I want to have gathered together and put in a single column? And I want to take ozone, wind, and temp, and I want to put them into a single column. Well, if I take ozone, temp, and wind and put them into a single column, that variable is going to need a name. So the second thing I'm going to need to specify is the name of this new variable that I create by taking these guys and shoving them into a column. When I take these guys and shove them into this column, all of these numbers here go along for the ride, and they come in as an adjacent column. And that adjacent column is going to need a variable name. So that's the third bit of information that I need to provide, is the variable name for the column that's created when the values of the body here go into that new column. So here's the code to do all of this. I'm going to create this new data frame called new data based on air quality 1, and the function I'm going to use is the gather function. So there's the gather function there, and there's its open parenthesis. Oops. There's its open parenthesis, and there's its closed parenthesis. And there's 3 bits of information that I'm requiring. I could put them on a single line, but to make things easier, I'm going to put them on 3 separate lines separated by commas. So the first thing is, what are the variables that I want shoved into a column? I want the variables ozone through temperature shoved into a column, so that's what I put on the first line. Now in this case, everything's convenient because ozone, wind, and temp are all side by side. What happens if they weren't side by side? I could do this concatenate function to identify a vector of the variables that I want taken together and shoved into a column. So, my gather function, the first thing is the variables that get put into the column. The second thing, I use the R keyword key to specify the name of that new variable that I just created. So by saying key is equal to parameter, I'm going to have that variable name parameter. And the third thing I require is the name of the column that is going to contain the values in this newly created variable. And the way I specify that is by value equals, and in this particular case, I've said y. That's why we have the y right here. I can reverse the process. I can reverse the process by starting off with this new data and recreating the original data air quality, although in this case, just to keep things simple, I'm going to refer to it as air quality 2. So I'm going to begin with new data, and I'm going to move in this direction from wide to long format. And the function I'm going to use is the spread function, and there's its open and close parenthesis, and it's going to take two arguments. First thing I have to say is, okay, I need to name the variable. I need to name the variable in new data that has the different levels, each of which, in this case, ozone, wind, and temp, I want spread out to be variable names. So within my spread function, I say key equals parameter, and as a consequence, R looks at the variable parameter, sees it's got these three different levels, and makes three variables out of them. Next question is, okay, I'm going to have ozone, wind, and temp, but what goes in the body of the table? Well, actually, I've got some choices. I could have a whole bunch of 5s, I could have 1s, 2s, and 3s, or I could have these values here. Well, of course, I want these values here. I want the values associated with the variable y. So the second thing I need to tell R is, there's my R keyword, value equals y. And so what that means is, what's going to go in the body of the table is going to be the variable y. Now, switching topics again to talk about this concept of binning. And this is very much an overview slide. So I'm going to begin with a very simple data frame. It consists of just two variables, cylinder and city. And where I want to wind up with is this summary binned data frame that looks like this. And so it's going to have this new variable called bin. And this new variable called bin is going to be based on city mileage. And it's going to have two intervals of equal width. First one goes from 20 to 25, and the second one goes to 25 to 30. And those bins, as I said, are based on city mileage. So if we look at this data frame, and the values of city mileage, and these bins that are based on city mileage, we can see that this record here, the 20, the 22, the 23, and the 24, they all fall in this first bin. It goes from 20 to 25, and there's 4 of them. And if you were to calculate the average city mileage associated with those 4 records, it would be 22.25, and the average number of cylinders associated with those 4 records would be 5.5. Now let's consider this second bin that goes from 25 to 30. Which records would fall into that bin? It would be this one, and this one. So there's 3 records that fall into this bin. On average, their city mileage is that, and the average number of cylinders is 6.0. So that's our goal, is to go from here to here. In order to do that, we're going to have an intermediate data frame that looks like this. And this intermediate data frame is going to have this new variable called bin. And in terms of the features of bin, is first of all, bin is going to be based on city mileage. So bin is going to be based on city mileage. Second feature of this variable bin is that we need to indicate the number of bins that we want, and we want 2 bins. We want 2 bins. And the final thing we have to indicate is the type of bins we want, and we want bins with equal intervals. So in other words, the difference between 20 and 25 is 5, the difference between 25 and 30 is 5. So, how are we going to do this? Well, in terms of the type of bin, we want bins of equal width. And so we're going to get bins of equal width by the choice of the function we use to create those new bins. And we're going to use the cut interval function, and that will give us bins of equal width. And then we tell R we want 2 bins of equal width based on city mileage. And so what does R do? R comes down here and looks at this and says, okay, let's think about city mileage. The minimum value is 20. The maximum value is 30. So if Peter wants 2 bins based on city mileage with equal widths, then 30 minus 20 divided by 2 equals 5. So it creates those 2 bins, 20 to 25, 25 to 30. Now, it's kind of a fine point, but if you look very carefully at these bins, notice here you've got a square parenthesis, and notice here there's a round parenthesis. That gives us an indication of what R is going to do if it should have a record that has a value of city mileage of 25. It's going to go into the bin that has the square bracket as opposed to the one with the round bracket. So, again, we're thinking of this as an overview. We're going to use the cut interval function, and it turns out we're going to use it in conjunction with a mutate function to generate this new variable bin in this intermediate data frame. So, once we've got this intermediate data frame with this new variable bin, going from here to here, by now it should be pretty obvious what we're going to do. We're simply going to group by bin and use the summarize function to create these summary statistics: count, average of city mileage, average number of cylinders. So again, this is another overview slide, and it focuses on the different types of bins, and the idea is we can have bins with equal widths, with roughly equal numbers of records in each bin, or user-specified bins. So we've got these 3 different examples, and they're all the same in the sense that they've got the variable bin, and the variable count, and the variable city average, and the variable cylinder average. And so we can see here in the first instance that since the least value of city mileage is 9, and the maximum value of city mileage is 35, if we want to create 5 bins of equal widths, those bins are going to have a width of 5.2. So we've got these different bins here, all of which have an equal width, which is 5.2. In this case, we want an approximately equal number of records in each bin. And so the output here shows an approximately equal number of records in each bin. And finally, in this last example, we're going to specify that we want these particular bin intervals. So now we're actually going to get into some code. So if we want bins who have equal width, the function we're going to use is cut interval. And if we're going to create this new variable called bin, then we're going to have to use the mutate function. So to accomplish our goal, which is to produce the ultimate summary data frame, there's our ultimate summary data frame, it's really a 2-step process. So we're going to start off with MPG. We're going to use mutate to create, and the name of the new variable is bin. We're going to use the cut interval function because that'll give us bins of equal width. We have to specify 2 other bits of information: the variable one, which is base, which is city, the number of bins, which is equal to 5. So once we've completed this step, we have this data frame, 234 records, and now this new 12th variable called bin. And once we're at this step, getting to here is just the same thing we've seen many times before, is with this block of code here. Group by together with summarize. And as always, how many records we will have? We'll have 1 record for each level of bin. So if we've got 5 different values of bin, we're going to have 5 records. How many summary statistics? We're going to have 4. We're going to have bin, we're going to have count, we're going to have city average, and we're going to have cylinder average. Now we've got a different type of bin. Bins based on roughly equal numbers of observations in each bin. And where this block of code differs from the previous block of code is really only in the first step. When we use mutate to create our new variable bin, now the function we're going to use is cut number, because the cut number function will give us bins of roughly equal number of observations. As before, it's based on city. We use a slightly different keyword. We use n, But again, we specify the value as being equal to 5. So at the end of that step, we'll have this data frame that has this new variable called bin. And these bins are going to be bins with approximate number of observations in each bin. The second step here is the same as the second step in the previous slide. We group by bin. Group by bin will give us 5 records associated with the 5 different levels of bin, and we'll have these 4 variables: bin, count, city average, and cylinder average. And finally, to get user-specified intervals, as before, we use the mutate function to create this new variable bin, but now the function to create those bins isn't going to be cut or cut interval. It's just going to be the word cut number or cut interval. It's going to be cut, and we're going to, as before, specify the variable upon which is braced, which is city, and also what we're going to do is specify where we want those breaks to be. So we use the keyword breaks, and then we'll have equals, and then we'll have a vector. So there's C, and we'll list the breakpoints that we want, 8, 15, 22, etc. So at the end of this first step, we'll have this data frame here with 234 records, this new variable bin that's going to have, if we specify 8, 15, 22, 27, we're going to see things like 15, 8, 22, etc. So once we have this data frame, as before, we just group by bin, use the summarize function. We'll have 5 records associated with the 5 bins and the 4 different variables as before. So this is just a summary slide that compares what was shown in the previous 3 slides. There's our 3 ultimate data frames, our summary binned data frames, and there are 3 different types. If we want types with equal widths, we begin by using the cut interval function. And if we want ultimately to have bins with approximately equal numbers of observations in each, then we use the cut number function. And if we want bins with specified intervals, then we use the cut function. So to get these 3 different outputs, the difference is in the first step. The second step, here, here, and here, is always the same. Group by bin and generate the 3 different summary statistics. And the idea here is that the bane of our existence is that oftentimes we're going to have missing data. So if you've got missing data, what you want to do is enter it in your data frame as NA. So when you make your Excel spreadsheet, put it in as NA. So let's say you've got a tiny little R data frame that looks like this, and you want to get rid of this record. What you might think about trying is something like this. Try to filter to get rid of the NA. Try this way of filtering, try this way of filtering, and what all this text is telling you is don't bother trying. It isn't going to work. The way to deal with missing data is in your Excel spreadsheet, add the data as NA. And then once that Excel spreadsheet has been brought into R, R has these 4 particular functions that are specifically used to cope with missing data. So you use these 4 functions. Don't try to code using some of those functions that we saw earlier. So let's go over some of those specific functions that are used to deal with NA, beginning with NA omit, which is a really heavy hammer, which essentially will eliminate any record in the data frame that has an NA anywhere. So we start off with DF, and then hit it with the hammer NA omit. Any record that has any NAs gets discarded. So this guy gets discarded, this guy gets discarded, this guy gets discarded, and we're left with that. Is NA. That's the next function. And is NA performs a logical test. It returns either true or it returns a false. And it depends on the value of X. So if X actually is NA, then the function returns true. If X is not NA, then the function returns false. And the flip side of is NA is the thing is not NA. And so the key thing to note is this exclamation point here that essentially reverses the is NA and makes it is not NA. So the logic is just the reverse to what we just saw. So it returns a value of true if it's not NA and false if it is NA. So here's our goal. Our goal is we're going to start off with df, and what we want to do is create df1. And specifically what we want to do is these three guys here that are NA, we want to make those into zeros, but all the other NAs, we're just going to be content to leave them as they are. So the code that we're going to do to make that happen. So we're going to use the mutate function. And inside that, we're going to have the if-else function. And let's think about how this if-else function works. We saw that before. Begins with a logical test. And if the logical test is true, then it returns this value. If the logical test is false, then it returns this value. So think about what happens when we use the if-else function. So the if-else function, our logical test is NA x1. So what does this do? It evaluates the variable x1 for every record in the data frame and returns either true or false depending on whether x1 actually is NA or not. So if we come back here to our original data frame df and we think about the output from our if-else function, is x1 NA? False, because it's a 7. True, 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 because it's an NA. So that's what this NA function is going to do. The is NA function is going to do. Now, let's think about what happens after that. If this function is evaluated and it's found to be true, in other words, we're thinking about these three cases right here, where the is NA function returns a value of true, then what is x1 going to be equal to? X1 is going to be equal to 0. So in these three cases, x1 is going to be equal to 0. What happens if the statement is false? What happens if x1 is not NA? What happens if x1 is not NA? If the truth condition is false? Then what does x1 equal? x1 is going to equal x1. In other words, x1 is going to remain the same. x1 is going to remain the same at 7. We're once again going to use the is NA function, but now instead of combining it with mutate, we're going to combine it with filter. And our goal is to start off with df. And what we want to do is come up with df1. And the whole idea is we want to retain only those records where x1 is NA and x2 is not NA. So we're going to start off with df, and we're going to do 2 filtrations. The first is we're only going to retain those records for which x1 is NA. So at the end of this first step, we'll retain only those records for which x1 is NA. So at the end of the first step, we'll have retained these 3 records. Then we, after the piping operator, retain only those records for which x2 is not NA. So of these 3 records, which one is it the case that x2 is not NA? It's these 2 guys here. These 2 guys at the bottom are the only ones that are retained. So in this slide, we're going to use the function NARM to ignore missing values. So we're going to start off with a very simple data frame called df. There it is. It's got 2 different models and the highway mileage associated with each. What we want to do is make a summary data frame that shows for those 2 different models what the average highway mileage is going to be. And the fly in the ointment is this value here of NA. So based on everything we know so far, we'd probably try to use some code that looks like this. So we'd start off with df, and we would group by model. So if we group by model, how many records are we going to have? We're going to have 2 records in our ultimate data frame because we've only got 2 different models in our original data frame. And how many variables are we going to have? We're just going to have 2. We're going to have model and we're going to have highway average. Model and highway average. But here's the problem. When it goes to calculate the average of these 3 values, it has no idea how to calculate an average that includes an NA. So in the resultant data frame, we get this NA here, which is not what we want. Really what we'd like to have under these circumstances is we'd like to ignore the NA, average the 20 and the 10, and have a value here of 15. And so the way we do that is really very simple. The code is exactly the same as before. It's just that when we use our summarize statement, not only do we say that we want to take highway average as the mean of highway, but we also add within the parentheses associated with the mean function, NA.rm is equal to true. In other words, NA remove is equal to true. So any value of highway that has an NA in it is going to be ignored. And so as a consequence, this value is ignored. The 20 and the 10 get averaged into the 15.